So for today's class, what we are going to talk about is generative models for graphs, right? So far we were working under assumption, or we talked about methods where we said a graph is given and we want to do some modeling, learning, prediction, community detection on top of it. What we are going to look at for the next two lectures is a different problem. It is a problem about how do we generate a graph, right? How would we generate a synthetic social network? How would we generate a synthetic economic network? How would we generate a synthetic communication network, right? What are some of the processes that would allow us to generate these types of graphs, right? The way we can do this is that we want to generate realistic graphs using generative models, right? So the idea will be that we are given a graph generative model, and we want to be able then to generate a synthetic graph that is somehow similar or matches the real graph. So this is what we would like to do. So why do we want to do graph generation? Why should we care? First is that we want to understand how real graphs form, right? So these generative models can provide us insights about what kind of processes take place, let's say in social science, in humans, when we create our own social networks and social connections. It allows us to make predictions in a sense, how do we expect this graph to evolve in the future? Synthetic graphs are also very useful because they allow us to understand various kinds of processes that lead to generation of new graphs, and then we can use them as data sets for understanding corner cases and understanding the performance of various kinds of graph methods. And the last is about anomaly detection, in a sense that we many times require a null model, a model that would say, this is what I would expect, this is the network I would expect, let me compare it now to the real world network and see what the differences are, right? So we want this type of null models to then be able to have a reference point for what is expected, and then whatever real data we have, we can kind of compare it to that expected reference point, to the null model. So the roadmap for graph generation and for the lecture today is the following. First, I'm actually going to talk to you about properties of real-world graphs, right? Because when I generate a graph, I want to fit some properties, I want to match some properties of the real network. And the question is, what properties are interesting and what properties should we try to match? And then I'm going to talk about the second part of the lecture about traditional graph generative models, where basically each comes with a different set of assumptions. These models are relatively simple, but they come up with a lot of insight and they really allow us to kind of understand the network formation. And then next week, Tuesday, I'm going to talk about deep graph generative models, where we want to learn the graph formulation process from data. And this is what we are going to cover in the next lecture. So today's lecture won't be kind of machine learning flavor. It will be more about traditional graph generation and a lot of cool insights. And then next lecture will be thinking about graph generation as a purely machine learning process. And of course, there is value in both. There is value in formulating things as pure machine learning problems, where you say, I want to predict the graph. And there is also value in generating graphs through these traditional models, because that comes up with a lot of theory, a lot of insights, and much more kind of inductive bias into underlying processes that could be taking place in these networks. So the plan is to ask first, what are some of the important properties of networks that, let's say, these generators should match, or that we can compare the generated network and the real network? And in particular, we are going to characterize graphs. We are going to measure graphs according to these four different properties. First, we'll call degree distribution, clustering coefficient, connected components, and the shortest path lengths. We have introduced some of these notions already at the beginning of the class, so let's do a quick recap. So first, degree distribution. Degree distribution simply says what is the probability that a randomly chosen node will have a given degree. Simply this is just a normalized count, right? You say it's in some sense a normalized histogram where you say, for every degree k, I want to ask what fraction of nodes has that degree. And I can simply plot degree versus fraction of nodes with that degree. And I can think of this as normalized histogram, or if I ignore this factor n, then it's simply a histogram of the count versus degree, right? How many nodes have a given degree. That's what is called degree distribution. The second thing we already talked about is clustering coefficient, which is all about trying to understand how connected are the neighbors of a given node. And in particular, we say clustering coefficient of node I is simply defined twice the number of edges between its neighbors divided by the degree of the node times the degree of the node minus 1. So clustering coefficient will have value between 0 and 1. And the reason why it is this way is basically saying I have k neighbors. So k times k minus 1 divided by 2 is k choose 2. It's number of possible pairs of neighbors you can select. So this is the total number of edges that is possible between a pair of nodes, a pair of neighbors of a given node with degree k sub I, and e sub I is actually the actual number of edges that occur, right? So if I have no edges between the neighbors, then clustering coefficient is 0. If I, let's say, have 3 out of 6 possible ones, then clustering coefficient is 1/2. And if I have all the 6 edges between the 4 neighbors that are possible, then my clustering coefficient is 1. And this is now defined clustering coefficient of a given node. Now, if you want to do the clustering coefficient of an entire network, what people usually do is they simply compute the average clustering coefficient across all the nodes, or they define, or they actually plot the distribution of clustering coefficient values. So those are 2 ways how to characterize this notion of how many triangles, how often friend of a friend is also a friend, right? You can say basically how likely am I to see this kind of edges between pairs of nodes that have a friend in common. And in social networks in particular, clustering coefficients tend to be very high because of this triadic closure that we have discussed in the last lecture about community detection. So these were the first 2, degree distribution, clustering coefficient. The third one we will look at is connectivity. And in lecture 1, we defined this notion of the connected components in the graph. And we said that one thing how we can simply characterize connectivity is to ask what is the largest connected component size, right? What fraction of nodes belongs to the largest connected component? So if I have some graph that it may not be connected, I'm asking what fraction of nodes are in the largest connected component, where connected component is simply a set of nodes that can reach each other, let's say on an undirected network. The way I find connected components is by simple breadth first search. And I would say that, giant component exists if this largest component is large. I know more than half of the nodes belong to this largest connected component. And then the last thing that the way we are going to characterize networks is through what is called shortest path lengths, or the notion of diameter. So mathematically, we define the diameter of the network as the maximum shortest path distance between any pair of nodes in the graph. So you take, essentially to compute it, it would mean take any pair of nodes and find the shortest path between them. Now the problem with this maximum is that you can have a long string of edges somewhere, and that will severely increase your diameter of the graph. So for real networks, you want to use some more robust measure of the diameter, for example, average shortest path length, where you say, let me go over all pairs of nodes I and j that are connected, and let me compute the average shortest path length between any pair of nodes. Many times if the graph is disconnected, then the shortest path length between 2 nodes that are in different components is infinite. So you would only do this over the largest connected component, or you would ignore pairs of nodes that are not reachable from each other. But the idea is that you want to get some sense of how many hops it takes to get from one node to another on average in this network. So these are the now 4 different ways how do we mathematically, empirically characterize properties of a given network. And just for the for the rest of the lecture, I'm going to use one realistic large-scale network that we are going to characterize, and then we will say, can we come up with a generative model that could generate this network? So for example, what we are going to use is we are going to use a network coming from this chat application called Microsoft Instant Messenger. So this was like a WhatsApp, Slack type application before all these other services existed. You know, it had at that time it had around 250 million monthly active users, about 180 million actually engaged in conversations. There were more than 30 billion conversations over a month, so about 1 billion conversations a day, and you know, hundreds of billions of exchanged messages. So what we can do with this now is we can take this communication data and we can represent this as a graph. So the way we are going to represent this as a graph is we are going to put, we'll have people, and we will connect to people if they exchanged at least one message. And here is actually the dots here represent the geographic locations of the users of this Microsoft Instant Messenger. And basically what you see is that they come from all over the world, except from North Korea, right? It seems that, you know, there was no users in North Korea, but everywhere else there are some users of this thing. So in total, we'll now have a network of 180 million people with 1.3 billion undirected edges between them. So now let's start characterizing this network. Let's start measuring it and say, how does this communication network of, you know, people all over the world exchanging short messages look like? So the first thing we can do is we can characterize the degree distribution. So what I'm plotting here is simply the degree of the node. This is number of different people a given node exchange messages with in a given month. Times, and on the y-axis is the number of such nodes with such degree. So I plot the count, so it's probability times the total number of nodes. So it's kind of an unnormalized histogram, right? What do you see? You see this super funny, strange, however you want to call it, interesting histogram, right? It seems that basically there is this huge number, right? Like notice these dots here of nodes that have the degree very close to 0. So basically you have a lot of people that only communicate with, I don't know, 1 to a couple of different nodes. And then it seems that you have all these other nodes here that have very large degrees, but you know, there's very, very few of them, right? For example, you know, you have maybe only one person that talks to 2,000 other people, and the person or the bot or whatever this thing was that talks to the most people was about 6,000, right? So it means out of 180 million people, there is one node whose maximum degree is only 6,000, right? Out of 180 million possible people to talk to, this bot only talks to 6,000. So what is very interesting is that this histogram is kind of very much axis aligned, right? It seems a lot of people or a lot of nodes with super small degrees, and you know, just one node, one count for every degree that is you know, higher than just, you know, this super small number. So this does not seem this plot does not reveal too much. But what you can do is you take this same data, but you just plot it differently. The way we are going now to replot this data is we are going to replot it on logarithmic scales, on logarithmic axis. So what we did now, it's exactly the same data, the same counts, the same degrees, but now this axis is logarithmic, right? Here is 10, here is 100, here is 1,000. And now all of a sudden you see this very nice shape, right? You see that basically I have majority of the nodes, yeah, this is 10 to the 7, so that's, you know, 10 million. 50 million nodes that, you know, have degree 1, 2, 3. So large majority of the nodes have degree less than 10. And then you see how here at the end we have very few nodes, you know, maybe 1, 2 nodes for each degree above several hundred. And the largest degree here I said is 6,000. So now you see this beautiful pattern appeared that before was not obvious at all. Like when I plot this on linear scales, just the histogram, it's just axis aligned. I don't even know how to interpret this. Right here, now on same data, just the axes are different. I'm basically plotting log degree versus log count. I see this very nice shape. This kind of what is called a heavy-tailed or a power law distribution that people like to call these types of shapes. So the second thing is, how about clustering coefficient? If we take this network and compute clustering coefficient, we find out that the clustering coefficient of this network is 0.11. So it means that 11% of the neighbors are connected with each other, and that may seem a little, but it's actually a lot. And the reason why this is a lot is because you have these super large degree nodes, right, that have a lot of possible connections between the friends. Actually, it turns out that 0.11 is quite a lot. Right now, it seems like, the clustering coefficient is between 0 and 1. 0.11 is kind of closer to 0 than closer to 1. So it seems that clustering of this MSN network is low. But because we will have null models, we are actually able to establish that the clustering is actually quite high. So let me now tell you why 0.11 is high and why is it not low, even though it seems kind of a tiny number. So this is what we are going to figure out. So this was clustering. Now the third metric was connectivity, right? How big is the largest connected component? And what I'm plotting here is the size of the connected component, how many nodes belong to a given component versus number of components of such a size. What do you see is that the largest connected component has about 200 over more than, right, this is 10 to the 8 is 100 million. So this is, almost like close to 200 million. So pretty much 99.9% of all the nodes belong to the largest connected component. So the network is connected. And of course, then we have, some small number of very small components of, 20, 30 nodes all the way to, let's say 1 million of nodes that are isolated. So connected components of size 1. So this means that our graph is well connected with a very small number of very small isolated islands. But the giant component is definitely there, and 99.9% of all the nodes belong to it. And then the last thing I want to mention is the shortest path length. So here is the distribution of shortest path lengths between different across pairs of nodes. So I ask here how many pairs of nodes are at shortest path distance 5, how many are at shortest path distance 10, and so on. And here the y-axis is logarithmic. So notice that most pairs of nodes are reachable with each other in around 5, 6, 7 hops. So it means actually that the average shortest path length of this giant network of 180 million people living all over the world is only 6.6. And it turns out that you can reach 90% of the nodes of this network on average in less than 8 hops. So it takes you 8 friendships to get to 90% of the nodes. And just to give you another way how you can think of this is to say, let's start breadth first search at a given node, right? So at 0 steps, it is 1 node. Now this node has degree 10, so at step 1, there is 10 other nodes I can reach, right? And these 10 nodes have further connect to other nodes, so at step 2, I'm at 75 nodes. And notice how the number of reachable nodes increases. And here, for example, at steps 6, 7, and 8, I can reach 28 million, 80 million, 52 million, and then again you see how this quickly decays down, where at hop distance 25 I could still reach 3 more nodes. So notice again basically this kind of shape here demonstrated by this single node example. So this is what I wanted to show in terms of the shortest path length, right? It's even though our network is massive, the amount of the shortest path lengths tend to be very, very, very small. And this is what is called the small world phenomena. right? That basically, even though the network is large, the diameter, the shortest path lengths are actually quite small in these networks. So what we have seen so far is that there are key properties of this messenger network, right? The degree distribution is heavily skewed. Average degree is about 14. Clustering coefficient is 0.11. Connectivity has one giant component with 99.9% of the nodes, and the average shortest path length is 6.6. And as I give you these numbers, right, you should be asking yourself, are these values expected? Are they surprising? You know, should I make fuss about it, or, you know, we just forget about it? Like, is it interesting? What does this teach us, right? And in order for us to determine whether this is interesting, is that we need a null model. So basically what we are going to look at next is different null models on which we can make these same measurements and then be able to say, aha, you know, messenger network has high clustering coefficient. Messenger network has, I don't know, low average path length or something like that, because we'll have this reference point. So what we are going to talk about next is talk about these reference points, these types of models.